Guys, so, excuse me, sorry, great start. So this one is going to be the math review video. I'm going to go over probably about 5 to 10 minutes of the most important math stuff we've covered so far. Obviously, I would have greatly preferred this to be in an in-person kind of interactive setting so that you guys can ask your questions as they come up, but we're all having to make do with the situation as it's unfolded. As always, feel free to shoot me emails if you have quick questions. I can't promise I'll respond super quickly. I very well may be sleeping or whatever, but wanted to get something out to hopefully give some guidance. So, first thing is the idea of sets. Sets are defined kind of circularly as collections of mathematical objects. You can think of them as kind of an empty bag that is only defined by the stuff in it. We don't care about the order of the stuff, we only care about what's in there. For that reason, we don't repeat elements, so the set 1, 1, 2 is equal to the set 1, 2 in our typical convention, because we wouldn't repeat these elements in a set. We also will not, we also will not care about the order, so 1, 2 is the same set as 2, 1. Now, one more thing to touch on, this is called set builder notation. And it comes in two parts. It's essentially a type of object and the condition it has to meet to be included. For example, one we might have seen is, let's say, the set, I guess we'll think of it this way. We'll say the set of dogs, we'll call that D, such that D is a labradoodle. And this gives us the set of all the dogs that are labradoodles. To give a less nonsensical example, we can say the set of all positive real numbers, we can write that as the set of all x in the set of real numbers such that, that's the such that x is greater than 0. And that's how we can write that. That's the set builder notation. You'll see that come up a decent amount. Yeah, and I'm going kind of quick because I anticipate most of these things you'll have already known, but nonetheless, not bad to hit on them again. So, next thing, we're going to touch briefly on vectors. So, without going the physicist approach, there's the whole magnitude and direction way of a vector, but the way that we like to think of them a lot of times is a list of n numbers. For example, we can do 1, 2, 4. Excuse me. That's a list of 3 numbers, obviously, and we can extend that into however many numbers we want. I don't know, 100, or I don't know, 1, whatever. And the way we typically denote this is we could say a vector x consists of x1, x2, all the way up to however many it has. And if you haven't had me explain it before, this arrow is just a way to denote that this variable is a vector. Not everybody uses it. You'll also sometimes see boldface written to denote vectors, but there we go. Now we say a vector with n components lives in Rn. We say that it's an element of Rn. That's what this means, is an element of. Rn here is the set of n tuples of real numbers. So basically, in fancy words, the set of vectors with n components in them. So for example, the vector 1, 1 is an element of R2. And notice here this is a vector, so the order very much does matter. The vector 1, 3 is not going to be the same as the vector 3, 1. So, because there are some sets we use all the time, we give them names and names and symbols that are specific to reference them. So the first one we just got to is the real numbers. Rn is the set of n component vectors. So R4 is the set of vectors with 4 components. We say R plus n is the set of vectors with non-negative components. And we say Rn plus plus is the set of vectors with strictly positive components. So those are some of the more common ones that you'll see used in this course. Next up on the list is going to be dot products. It's something that should feel very familiar by now, but it never hurts to go over it. If x and y are vectors, which I'll define this way, we define x dot y as x1, y1 plus x2, y2 plus all the way up to xn, yn. Now this is going to output a single real number. It will not output another vector. Don't make that mistake. It's going to be each of the components multiplied together and then add them all up. Now, it follows here that in order to be dot producted this way, two vectors have to have the same amount of components. For example, it doesn't make sense to try and do the vector 1, 1 dotted with the vector 3, 4, 5 because the components don't match up. There's this extra one. So that's the idea of a dot product. Again, going quick, but if you have any questions, shoot me an email. I'm just assuming that this up to now feels familiar, but just want to touch on everything to be sort of all-encompassing. So next thing we'll touch on is the idea of a gradient. So just in general, I guess I'll touch first on functions of multiple variables. These vectors that we've now defined, we can put them inside of a function to get a single real number. We say this function takes in n variables, or alternatively, it takes in a vector in Rn, however you want to phrase it. And oftentimes we're curious to figure out how this real number output changes as one of the variables changes. Similar to how you might have y equals f of x in calculus 1 and you want to find dy dx. In this, we're wanting to find the derivative of f with respect to, say, x2. The way we denote that is the partial derivative of f at all of the points over the partial of that variable. And the way you find this is you hold every single variable, x1, x3, x4, all the way up to xn as constants when you're differentiating, except you differentiate with respect to x2. You treat that one as your variable. And a gradient is the idea of taking each one of these partial derivatives and putting them in a vector. So if f is, say, x1, x2, x3, it takes in 3 variables. Then we define the gradient of f as the vector of these partial derivatives. So that's kind of a quick overview of the idea of a gradient and multivariable functions. Functions like these are going to take in multiple inputs and give out a single output, and that's why we have to consider the partial derivative instead of the regular derivative, and we often want to consider gradients, which are vectors of these partial derivatives. So this is part one. In the next part, we're going to go more into the Kuhn-Tucker conditions, the envelope theorem, and some other fun stuff.